This is illustrated in this picture. The sender creates a message or plain text. The sending OpenPGP generates a random number to be used as a session key for this message only. The key here shows the session key. The sending OpenPGP encrypts the message using the session key. The session key is encrypted using each recipient's public key. The encrypted message and the key, encrypted key, is sent across to the receiver. The receiving OpenPGP decrypts the session key using the recipient's private key and decrypts the message using the session key. If the message was compressed, it will be decompressed. Messages are generally compressed before encryption in order to reduce the size of the data that has to be sent over the network and to remove redundancy that could help cryptanalysis. This picture illustrates how authentication and integrity checking can be done via digital signatures in using OpenPGP. Here you can see that the sender creates a data or message. The sending software generates a hash code or message digest of the message. A signature is generated from the message digest using the sender's private key. The binary signature is attached to the message and the two together are sent across. The receiving software keeps a copy of the message signature. The receiving software keeps a copy of the message signature. It generates a new message digest from the received message. It decrypts the message's signature using sender's public key and verifies it with the generated message digest. If the verification is successful, the message is accepted as authentic and the correct hash proves the integrity of the message.
GPG can be used also for symmetric encryption. In symmetric key encryption using GPG, we have to issue the command with symmetric option to generate the encrypted file, and to decrypt we have to use decrypt option. After entering the command for encryption, system will ask for the passphrase. This passphrase will be acting as the key. After the encryption, the system will generate a .gpg file, which is the encrypted file. Optionally, we can enter a -a option so that the generated file will be in a more readable form. Now we can transfer the output file to the recipient and he can read the content by decrypting the file. While issuing decrypt command also, the system will ask for the key. We have to type in the key correctly to decrypt the file. Now we can use these generated keys to do the encryption. In the terminal, by adding an encrypt option to GPG command, we can do the encryption. Additionally, we have to give a -r option to specify the recipient of the message. The system will generate a .gpg file which we can transfer to the recipient. Also, we can add a -a option to the GPG command so that the generated file will be in more readable form. Now at the receiver side, we can issue GPG command with decrypt option to decrypt the message.
Key server is a central repository of keys. You can upload your public key to key server. Once you upload the public key to the server, everybody else can download the key from the key server using the key ID. You can only upload your own public key to the key server. That is, you cannot upload a public key if you do not have the corresponding private key. To send a key to the key server, the send keys option can be used. The key server option is used to specify the name of the server to which you are uploading the key. While sending the key, we must use the key ID and not the key name. To retrieve a key from a key server, we use the receive key option. We must use the key ID instead of key name here also.
If you want to send an email to another person, you need to have his key. You can get his key either through a key server or through email or by any other means. However, the key should be validated either by you or somebody you trust. In PGP, there is no concept of a certificate authority. Every user can behave as a certificate authority, and he can sign keys for users they know directly. PGP allows you to sign someone else's key, and you should sign another person's key once you've verified that the key is valid. It allows you to accept the validity of a key of someone you have never met. For example, if Alice trusts Bob and Bob trusts Charles, then Alice can also trust Charles. This concept is clarified in this picture. The circles with a center dot identifies the key that is legitimate by you, and the arrows represent an arrow from X to Y represent that X is signed by Y. You can see that the keys of A, B, C, D, E and F are signed by you, and hence the key is legitimate by you. The users D, E, F and L are trusted by you, and D, E, F and L can sign keys on behalf of you, and hence the keys M, N, O, P, Q, which are signed by my trusted introducers, are also legitimate. The key H, which is signed by two introducers A and B, is also legitimate because a half shaded portion shows that the key's owner is partly trusted by you, and hence such a key should be signed by two partly trusted introducers. The keys I, J and K, although signed by C, are not legitimate because C is not a trusted introducer.
Here we give a brief demonstration of the web of trust in GPG. In the trust model used here, we need sign from a single fully trusted person or sign from three marginally trusted persons to make a key valid. A key can be signed using the --sign key option. After signing or importing a key, you should use the GPG with the --trustdb option to update the trust database. First, we demonstrate a full trust. Here, we first take an unsigned key from a file. Then we try to encrypt using this key. Here we can see that GPG generates a warning while encrypting the file. Now we upload the same key which is signed by a person we trust. Now when we try to update the database, we can see that the GPG asks us whether to trust the new person or not. We give the new person a full trust. After we trust the person, GPG will not generate a warning while using the key of that person.